Hey everyone, welcome to Rainmaker 3D. Today we're going to be diving into electronics. And so this is a great software that a lot of people don't know about. It's called Tinkercad. And Tinkercad has something inside of it that many people aren't aware of. And you can actually build real circuits inside of this software just like you would in real life with the same components and be able to test them. It'll draw schematics for you. It'll give you a bill of materials so you know exactly what to buy. I mean, it's really cool software. And so all you have to do is go to tinkercad.com, make an Autodesk account, and then join along with me and let's go to circuits. So just on your Tinkercad homepage, Tinker Circuits, and you'll come to this page and we have all sorts of different tutorials. And today what my goal is to go through every one of these tutorials, walk through them in real time. I've reset them so they should be the same on your screen, and I really would encourage you, follow along. It's free. This is a great way to learn electronics that I didn't have available to me whenever I was learning electronics in college during my electrical engineering degree. And so I'm going to walk through different principles like Ohm's law, what is voltage, current, resistance, and just talking through out loud as we do experiments. And I think it's just going to be a fantastic way for somebody who is truly a beginner to learn electronics for free, completely for free. You just need a computer to be able to tinker with electronics on Tinkercad. So I've got our first simulation set up, and what this is it's a very simple circuit with an LED. You're just making an LED turn on. So we'll hit start the simulation, the LED turns on. And so I'll walk you through the components here. There's a CR2032 3-volt coin cell battery, a resistor, 220 ohm resistor that limits the amount of current that goes into the anode of the LED and out of the cathode. And so an LED has an anode and a cathode. Essentially the way to think about a diode, which LED stands for light emitting diode, is a diode lets current flow in one direction only. So if we were to wire this backwards, it wouldn't light up because current couldn't flow the other way through the diode. And so what else is cool is you can change the resistance to change the brightness of the LED. So if we kick it up to 2,200 ohms or 2.2 kilo ohms, the LED is dimmer. If we completely delete the resistor and rewire the circuit and start the simulation, it gives us a warning that there's too much current passing through the LED, which could affect the lifetime of the LED. That's why you can take an LED and stick it on a 9-volt battery and it will spark up, but it does not spark up for long. It makes it very unhappy. So if we just come through and hook it up to a 9-volt battery, it explodes, because there's 915 milliamps of current, and this is exactly what would happen in real life if you did this. So it's a way to be able to blow up electronics without having to spend a lot of money. And so that's the first project that we have. So one project in the books. Let's move on to editing components. So in this one, we start out, you should see 3 blue LEDs over here. You've got 3 resistors that are in series. There's 2 different ways you can hook up components in circuits. You can either do in series with other components or you can do in parallel. So these 3 LEDs are hooked up in parallel and they have resistors in series to limit the amount of current passing through them. So let's go ahead and hit next. It asks us to change the colors. So we're going to change this one, the top one, to we'll go ahead and change it to red, and then yellow and green. And let's go ahead and start the simulation. So we go green light, yellow light, red light. So pretty cool. So you can also go ahead and step inside and see the code that's written. So there's 2 different ways that they code inside of Tinkercad. You can either do it with code blocks or you can do it with C++. Now I was trained in college on C++, so it's familiar to me. A basic rundown of what's going on inside this code is there's a declaration where you're setting up the pins with variables. So what are they called? So in this case we have pin 0, pin 1, and pin 2. So LED red is pin 0, LED yellow is pin 1, LED green is pin 2. They're set as outputs. You can set pins on an Arduino Uno, which is a microcontroller, to either be inputs or outputs. In this case, it means that there is voltage flowing out of pin 0, 1, and 2, and they are set to go on for 2 seconds. This is 2,000 milliseconds. You see these where it's yellow, that's comments. So anytime you see the 2 backslashes, that's a way to be able to write comments. And so it turns green for 2 seconds, then it goes yellow for 1 second, it turns the red low, which means off, and then high is on. So it goes yellow for 1 second, and then it goes red for 3 seconds. You could change this and make it go a whole lot faster if you edit the code. And we'll mess around with editing code in some future ones. So let's go to wiring components now. This is the 3rd tutorial. So in this case, we have a 555 timer circuit with a speaker, a capacitor, some resistors, and some push buttons. And so what we're going to do is we're going to connect the positive over here to the positive rail of the breadboard. A breadboard, you can see all of these are in line. So if you just energize any pin on a breadboard where it says positive or negative, then the whole rail conducts. And so we have positive and negative. And so now we'll go ahead and run the simulation. And when you click the different buttons, it generates different frequencies that go to the 8 ohm speaker. Pretty cool. So you can actually make sounds without having an Arduino at all, just with a 555 timer. And based off of the resistance value and the capacitor value, the RC, it will generate a different frequency tone. So each one of these resistors is a different level of resistance, which allows you to create different frequencies. So pretty cool, an RC circuit. That's important. We'll go over that in future videos. But basically, you have now wired your first circuit. So we'll go ahead and go on to the next lesson. Let's go back to the project pages here. Go to Tinker, go to Circuits, and let's go to Adding Components. So we'll start this. So what we have here is just a 3-volt battery. 2 AA batteries make 3 volts, and we have a motor. So we'll hit start the simulation, and so the motor starts to turn at 5,902 RPM. So now what we're going to do is we're going to add a photoresistor, which is a variable resistance that, based off of the amount of light going to it, will affect how much resistance is in the circuit. So right now it's drastically slowed down the amount of rotation in the motor, and if we increase the brightness, we'll see that the motor speeds up. And so if we take a multimeter, change it to resistance, and we take another photoresistor here, and we start the simulation, we'll see that as the amount of light increases on the photoresistor, the amount of resistance decreases. So that lowered resistance is allowing more current to flow through the circuit, and speed up the motor. So now let's move on to another project. We'll go back to the home page, Tinker Circuits, and let's go to introducing the breadboard. So we were slightly introduced to it whenever we had the 555 timer and the different frequencies. But what we're going to do now is create an RGB LED circuit. So we have the positive and negative rails, and then we have 1 through 30 of these different rails that each one of these pins are connected. But they are separated from each row. So each row is separate from the row above or below, but each one to the left and right of it is connected. So we're going to add a 9-volt battery. And so the other thing we can do is we can rotate components. And so I'm going to stick the battery, we're going to zoom out here a little bit. Stick the battery down here. So we've energized the positive and negative rail. And if we were to just add a multimeter here, set it up in voltage, we would see it says -9 volts. It's because it's wired backwards. So if we hook it up the other way, we've got 9 volts, right? So we are energized on our positive and negative rail. And so now what we're going to do is, I'm reading through this, so we're going to get the RGB LED. We're going to rotate it 90 degrees, and we're going to, they have it set on pin 13 through 16, so we'll go ahead and slide it down here. And then we have a resistor that goes from pin 14 to pin 18, and it's a 480 ohm resistor, so we change it from kilo ohms to ohms, 480, and then we'll go ahead and wire that to the negative rail. So their picture is a little bit different. Their resistor, we'll go ahead and flip it 180 so it matches the picture here below. And so now we'll go ahead and see that nothing has happened. Why has nothing happened? Well, right now there's no way to get power to the LED. So the circuit is open. So let's go ahead and keep reading. And we have what's called the ravine. So that is this part in the middle between E and F, between columns E and F. And so what we're going to do is we're going to get a push button. Push button. It wants us to rotate it 90 degrees. And we're going to put the push button on E1. So we have it on E1 and E3 and F1 and F3. So we're going to use this to trigger each pin of the RGB LED. And so now what we're going to do is we're going to go from positive to A1. And we're going to go from D3 down to D13. And we'll go ahead and start the simulation. Click the button, and look at that, it's red. So now what we're going to do is we're going to put 2 more switches. So we'll copy Control-C, Control-V if you're on a Windows computer, and we'll put that in E5. We'll just leave it push button 2, and then we'll Control-C, Control-V again, and we'll put that at E9. We're going to make some voltage jumpers You can hit escape if you click the wrong rail like I did. And we'll jump from positive rail to A5, and then from positive rail to A9. And we'll go ahead and make the wires match. So we'll make these jumpers purple. We'll make this wire red so we know it's the red LED. So now we're going to jump from C7 down to C15. We'll make this one blue, or turquoise is what they have. And then we'll jump from that's B11 down to B16. And we'll make that one green. We'll hit next. And now we'll start the simulation. If we click switch 1, turns red, switch 2 turns blue, and switch 3 turns green. So that's how you make an RGB LED circuit work with no microcontroller. So we have switch 1 red, blue, green. So pretty cool. And yeah, you can also make a bigger breadboard if you need more room. So now we're done with that project. So let's go back to Tinkercad and let's move on to the next tutorial here. So let's look at Ohm's law. We're going to go ahead and reset this tutorial and start it. So here's what's going to happen. Do you think this LED is going to blow up? I don't know. Let's see. So we start the simulation and bam! It's got 915 milliamps, almost a full amp of current passing through it. So V equals IR. So if the voltage is 9 volts and the current is 915 milliamps, what do you think the resistance is? Well, it's not very much. So we could figure it out mathematically, V equals IR. You could divide the I on both sides of the equation, so V over I equals R. And you could figure out exactly what the resistance of the circuit is of just the LED itself. And so I am going to, just for fun here, pull up a calculator. And we'll do 9 divided by 0.915. So it's 9.83 ohms of resistance because it's milliamps, so you got to do amps, so 0.915 amps of current. And yeah, so it's about 10 ohms of resistance for just the LED in this circuit. So it's rated for 20 milliamps. So if we were to do V equals IR, if we were to do V over I, and I being 20 milliamps, so 0.02, let's figure that out. So 9 divided by 0.02, what's that? 450 ohms. So we need a 450 ohm resistor to be in series with this LED. So we'll go ahead and let's grab a resistor and we'll make it 450 ohms. Hook it up to the positive side here. We'll go ahead and change those wires to red. And there we go. Look at that. So let's figure out, mathematically, is Ohm's law correct? Well, fortunately, there is a multimeter, and the multimeter can either read amps, voltage, or resistance. So we'll set it to amperage. Let's go ahead and delete this lead, and we'll go from the resistor to the positive side, and then the negative side goes to the anode. And so in order to measure current, your multimeter needs to be in series with your circuit. You can measure voltage in parallel with your circuit, but we need to be in the middle of the circuit with the multimeter in order to measure the current. So we're about 15.4 milliamps. So it's not quite 20 milliamps. So that's interesting. And what do you think is the reason for that discrepancy? Well, let's go ahead and see if we can measure the total resistance of the circuit. So we'll go ahead and we'll delete those two. And let's see if we can measure the resistance of the LED and the resistor. That's not quite right, is it? I screwed up. Let's see. We'll just make sure our circuit's working. Let's see if I can actually figure this out on the fly in real time, guys. So in order to measure resistance, we've got to be able to pull the resistor out of the circuit. So we'll just do a sanity check here, and we'll check and make sure that's 450 ohms. That's right. So then now we'll copy and paste an LED, and let's check the resistance on it. So what I think is happening is the difference from the theoretical is because of the LED and the wires. What do you think? That's just my thought. So let's continue, and let's change it to a 470 ohm resistor. And you notice that the colors change in the bands whenever we change the resistance. So if we were to change it to a 1 kilo ohm, notice that it's gold, red, black, brown. So if you want to learn more about that, we'll go ahead and click here, and it pulls up a Wikipedia page. And the gold is the tolerance. You've got a first band, a second band, and a multiplier. And so this chart's pretty important if you wanted to know the resistance of various physical resistors you have on hand. This chart, I like apps to be able to just put in the bands. It's a really easy way to do it. So let's go back to Tinkercad now. And we have finished up this experiment. Let's go on to the next one. So we have series and parallel circuits. So I've alluded to this a little bit. So let's look. We have, in this tutorial, we'll learn about two fundamental types of circuits, series and parallel circuits, and find out how to apply them to most efficiently light up multiple LEDs, because more lights equals more fun. So we have a single LED, we have two LEDs, and then we have four LEDs. So in the left-hand circuit, we have the resistor. So ultimately we go here, we're in series with the LED. It's measuring the voltage across the LED. We have another multimeter that is, this one is in parallel with the LED to measure the voltage. This one is in series with the resistor and the LED, and then finally the resistor goes to the negative side. So let's go ahead and start the simulation. So we have 2 volts across the LED. We have 13.9 milliamps of current flowing through the circuit. and we look over here and we don't have enough voltage across this LED to make it really light up. We have no current flowing in this circuit. And in this circuit, we have 10 milliamps of current running through this specific circuit. So the LED is barely turned on in the middle circuit. So typically, LEDs have what's called a forward voltage. So in this case, it needs at least 2 volts to be able to light up. So let's think about this. What could we do in order to increase the amount of voltage going through these 2 LEDs? Let's see. So I want to just, for fun, I don't know if it's going to get to it or not, but I want to just go ahead and add another battery. Let's add another battery here. And I want to see if it works. How about that? So we added a second coin cell battery in series, and it turned on both of the LEDs. I just want to try it. Something you can do. That's the cool thing with the software. You can just tinker around. And I would encourage you to. If, in case you're getting bored with me, hey, play around with adding batteries, blowing up LEDs. That's part of the fun of electronics. Hopefully you're not. Hopefully you're still tuned in. And let's see. Let's move on now. So we powered, in this case, 1 coin cell battery whenever they were in series was not enough because each LED was taking about 1.5 volts. So in this case, we've got about 2 volts going across each of the resistor and the LEDs. Now we have them in series and we're pulling 10 milliamps. So what's going on? Well, let's measure the voltage across one of these LEDs. So we'll go ahead and put another multimeter, and we'll go positive and negative. And we've got 2 volts. So there's a voltage drop from the 3-volt battery. And let's see if we can see that voltage drop with another voltage multimeter. And see if it's across this resistor. Where did the voltage go? So yeah, there's 2 volts at the LED, and then there's 0.6 volts across the resistor. So there's still a little bit of voltage missing. Let's go down here and see what that voltage is. It's still 0.68. So we've got a little bit of a voltage drop in the system. Let's measure the voltage across a different LED. Hook up the positive side of the multimeter to the anode, negative side of the cathode, and once again we've got about 2 volts. So whenever you go in series, you have voltage drops across each component, but it doesn't draw as much current. Whenever you're in parallel, you're going to have more current being pulled. So this battery is going to go dead faster than this battery because you've got 10 milliamps across 4 different LEDs. So you've got about 40 milliamps of current draw coming from this battery. Now, depends on how big the battery is in regards to how long it can stay on, but that's why your components go dead, like your car battery, different things, is because the amount of current that's being supplied in the circuit. So that is it for this project. let's go back and go to Circuits. And now let's go to these. These things are pretty cool. So these are microbit LED matrices. So we have a static LED example and a dynamic LED example. These things are completely new to me. So let's figure it out together. Let's learn how to make the LEDs light up and make an image using the microbit controller. If you're new to the microbit component, this is a great place to start. You'll use the code editor to create a simple program to tell the microbit what to display. Here in Tinkercad Circuits, you can explore the examples already placed on the work plane and build your own right next to it. The samples are here for a static image on the LEDs and a dynamic animated image with the LEDs on the right. So let's go ahead and click the Start Animation button in the top toolbar to watch the LED matrix light up. So we've got a smiley face on this microbit. And then we've got a pulsating heart. So let's go ahead and stop the simulation. And let's go to Library. Let's go to Microbit. And let's see here. We've got a light. And then let's click the code. We got microbit 1, so that's this one, and it just shows these LEDs. So let's give him a nose and see what that does. So now he has a nose, so that's pretty cool. Let's look at the second one, the dynamic one. So we have a start, and then it shows basically like a goalpost and then a heart. And it changes every 400 milliseconds or 0.4 seconds. So let's go ahead and watch that again. So what do you think we would do in order to add a new screen? Let's go ahead and place a Show LEDs. And let's make an X. And then we'll have it wait. We'll do milliseconds, 400 milliseconds. What do we think it's going to do? So it makes a goalpost, a heart, and an X. How about that? So that's pretty cool. So now let's go to back to our code, and we'll go to our new one. And what's it doing right now? It shows a plot bar that's reacting to the amount of light on the microbit controller. What if we wanted it to do something else? So let's go ahead and have it draw a square. And there we go. So that's how we can mess around with the microbit LED controller. So that's pretty cool. So what would you make with your microbit LED display? Would you make a static one, a dynamic one? I'll have to play around with that some more. So you can make all these different animations and have them loop. So that's a very critical component of programming, would be looping. So essentially in this case you're making a loop forever. You can make a loop for a certain amount of time. You can make it loop on a button click. You could make it loop on whenever it shakes or when a pin is pressed. So there's a lot of different things that we can do with these microbit controllers and I bet in a future one, we'll see what else they can do. So let's go ahead and go to Tinker Circuits. So we have 8 down, more to go. So let's go to the motion sensor and buttons. So this is a dice roll sample. So microbit motion sensor and buttons will explore a few of the inputs of the microbit here, including the accelerometer, which measures movement, and the physical buttons next to the LED matrix labeled A and B. So we have buttons A and B, and we're going to make a simple dice game in this case. So we drag a new microbit component into our work plane, and then we'll code it, select an input, select basic, and continue. So let's go ahead and check out the code here. Let's see if we can zoom in on this. So on shake, it'll clear the screen. It picks a random number from 1 to 6, and if it's 1, then it shows 1 LED. If it's 2, it shows 2 LEDs, 3 LEDs, 4, 5, and 6. Okay. Whoop. Whoopsies. There we go. We fixed it. And then whenever the button is clicked, it clears it. So let's just try it. So we'll go ahead and on shake. So we shook it and it rolled a 4. We click the button, it clears it. Shake it again, it was a 6. So that's pretty cool. So hey, maybe if you're playing Monopoly, forget the dice, let's do electronic dice. I don't know how well that'd go over in a casino, but hey, here with microbit electronics, we've got your random numbers covered. So let's read through this. So next you'll set a variable, which is a code block that contains a random number from 1 to 6. All right. So let's go ahead and zoom out on this, get out of the code, and we're going to do a new microbit controller because it's wanting us to make this from scratch. So we saw what the final result looks like. Let's see if we can make one from scratch. So we'll go ahead and delete that. Let's try this again. All right. I want to do a blue one. So we've got our blue microbit controller, and it's just wanting to show a happy face. But we don't want to do a happy face. We want to make a dice. So we have, what we need to be is on shake. So instead of on start. So let's go ahead and delete this, and drag out the on shake, and then clear screen. Set number, so we'll go to variables, create a variable, we'll name it number. So set number, and then we need to do to a random number, so we need to do math, so we'll do pick a random number from 1 to 10. All right. I think we're starting to cook with gas now, so we need to do some controls. So we need to do some if, else, and nest them. So as I am building this, I'm going to kind of talk you through it. So we have if else, and they're nested. So how do we make a nest inside of it? If true, then else. That's how, because we picked the wrong block. So let's go ahead and drag this to the garbage. We need to do the if true, then, and then the else. All right. And then we do another if true, then else. If true, then else. So 1, 2, 3, 4, 5. All right. So now we need to change this to 6. So it's going to pick a random number from 1 to 6. So we need to pick the control button, set number, leaving a blank spot under it. Now click and drag 3 more. So we need to have 1, 2, 3, 4, 5, 6 openings for numbers 1 through 6. So we need to go to Math and select a 1 equals 1 code block with pointy sides, which are designed to align with the pointy edges of the if true, then else code block. Drag 1 equals 1 block to the work plane inside the true spot on the if true, then else block, replacing it. All right. So 1 versus 1. All right. So the next, select variables in the top panel and drag number into the variable. So if number equals 1, then do something. Repeat the process a few more times to replace all the true pointy end blocks with comparators. So we are basically saying, instead of true, we want number to equal 2. And then we go back to math. If number equals 3, and then math, if number equals 4, if number equals 5, and then else. Because if it's not 1, 2, 3, 4, 5, then it's 6. All right. So dice have 6 sides. 1, 2, 3, 4, 5. You don't need to select a value for 6. So now we select an output and we do show LEDs. So 1. And then we do 2. Show LEDs. 3. Show LEDs. 4. Show LEDs. 5. And then if it's not that, then that means it's 6. All right. So it should look like this, and it does. We hit next. So on shake, it clears the screen, and let's see if it works. Oh, it does. How about that? Isn't that pretty cool? So now we add a button. So right now, it clears it when we shake it. But what if we just want it to be blank when button A is pressed, like this one? So we need to do an input, and we'll slide over here. On button A pressed. Then we do an output of clear screen. And let's start the simulation. So we shake it, clear it. Shake it, shake it, shake it, clear it. Shake it, clear it. So how about that? We've made a 6-sided dice simulator with microbit. Pretty cool. All right, so let's go back to circuits. And where are we at now? So let's go ahead and keep on trucking. Let's at least finish the microbits. And then I think in another video we'll do Arduino. All right. I do think these are a pretty clever way to be able to learn coding with block coding. Maybe a little bit easier than Arduino. So let's go ahead and drag a new microbit controller. So the microbit component has a few onboard sensors that give you some additional options. This lesson will show you how to use the light sensor and the temperature sensor. Ready to try them out? Is it getting hot in here? I don't know. Don't have the microbit set up yet to tell us. Let's just see what theirs do. So when it gets brighter, we see the level change of the LED display. And whenever on this one on the right, on the red one, what does it do? I don't know. Does it do anything? Ooh, 26. So it tells us what the temperature is when we click the button. That's pretty cool. All right. I bet this one's going to take a little bit. All right, we dragged in our new microbit. And let's go to plot bar graph of 0 up to 0 code block. All right, so we drag the LED up to see how it corresponds in the bar graph. So we're going to just read through this real quick and see what it wants us to do. I'm not sure why this says try the temperature sensor, because it's definitely the light sensor. All right, let's go back. So select the basic in the top. We're going to go to microbit 3. And right now, it's just showing a smiley face. So let's go to plot bar graph. Plot bar graph. Let's get rid of the smiley. Let's throw that in the trash. We'll drag it to the forever one. We'll drag on start to trash. All right, and then input. Let's click the light level. Light level. And the next one, we're going to type 225 over here. So light level up to 225. And now let's run our simulation, and I'll be darned, that was way easier than if you're going to code in C++, for sure. That is very easy. Cool. So now let's try the temperature sensor. So let's go ahead and so we're going to do basic on button A pressed, and we're going to do show number 0. Let's go ahead and look at this image here. So on button A pressed, show number temperature sensor. So let's change this. We'll go ahead and drag that into the trash. And now we need to do an input of temperature and into the 0. So our code looks just like that. And let's run the simulation and see if it works. So it should say 21. 21. How about that? 4 degrees, it shows 4. So this is actually, that's so much simpler than C++. That is very easy. So on button A pressed, show temperature in Celsius. Make it hot in here. So let's do that. 50 degrees. Cool. And yeah, that's pretty neat. So let's go back to our circuits. Go to Tinker Circuits. And let's go to external components. So we got 2 more to go, and then we'll make a second video whenever we go into Arduino, because we're getting close to about an hour long here. All right, using microbit with external components. Although the microbit has loads of fun onboard sensors, and you can also connect it to external components, let's try to add a simple component to the microbit to control the onboard LEDs. Find a microbit component from the library and drag it onto the work plane. All right. So we'll make our microbit. Let's drag a potentiometer, which is a variable resistor. Potentiometer. Next, you'll connect the component and the microcontroller first. Select the potentiometer and press the R key. Ooh. We rotated it 180 degrees. All right. And we hit next. Okay, so it wants us to go ahead and wire the middle pin of the potentiometer to pin 0. All right, and then we'll do the right pin of the potentiometer to the 3-volt pin. We'll go ahead and make that wire red to let us know that it is for positive voltage. Green is the signal wire. And now we're going to move terminal 2 to ground. So basically what this makes is a voltage divider. So the potentiometer has a specific resistance. In this case, it's 250 kilo ohms. And there's 3 volts possible. So in between the 2 legs of the potentiometer, you could be, for instance, well, I think this is better just shown instead of told. So let's just go ahead and show, because you may not know what a potentiometer is. So let's go ahead and just check resistance from one leg to the other, and then from one leg to the other. Show resistance. All right, so in this case, you see we're 250 ohms. The potentiometer swung all the way to the left, 0 ohms, and if we rotate it, you notice that they're both dead even, and then 0 on the right and 250 on the left. So it divides. It makes a voltage divider for the potentiometer. There's some good videos on YouTube that go more in depth on this, but let's get back to microbit. Okay, so let's go to the code. And right now it's just showing a smiley face. So let's go to code and throw that in the trash. And let's go to basic and plot bar graph 0 up to 0. Plot bar graph in the forever block. We'll hit next. Select input, read analog, pin 0 under input. All right. And we'll put that in the first 0. And on the second, the max value it can read up to is 1023. Why 1023, you ask? It's because of the amount of bits that this controller is capable of. In other words, how sensitive the reading is. So it's going to read from 0 to 1023. So there's 1024 bits of information that you can discern. So let's start the simulation. And it's not doing anything. Why? Well, let's look at the one that's actually done. We can see that it's plotting a bar graph. But ours isn't pretty. We messed up somewhere. Let's figure it out. Drag an LED from the library on the right. Well, hold on now. We didn't get it right. Let's look at microbit 2 and see. Right analog pin 1. Right analog pin 2. Huh. Well, we have the same code. Oh, read. Digital pin. We want to read analog pin. Let's try it now and see if that works. Yeah, okay, so we had digital pin instead of analog pin. That's what was wrong. So now we're the same as single component example. So now let's add a LED. So let's drag an LED from the library. And with the LED selected, let's go ahead and rotate it. All right. And then drag it under the microbit controller. Let's connect the anode to pin 2. And we'll change that to a green wire. And then the cathode to ground. Change it to a black wire. All right. And then we're going to get the hobby motor. We'll rotate it. And we're going to get a battery pack. Let's see. Can we get 2 batteries, please? So we got 2 batteries, and then we need a transistor. A transistor is a way to make current flow. So we've got a NPN transistor. And finally, we need a resistor. All right, so let's go from the positive end of the motor to the emitter. Okay, we'll make that one orange. And then we need to go from the negative wire to ground. We'll make that one black. And then we need to connect pin 1 to the resistor's base through the 1 kilo ohm resistor. So this is a signal wire, so we'll make it green. We'll make this little bit green. All right, and then we go positive to the collector side of the transistor. Now, what's a transistor, you might be asking yourself? That's a great question. A transistor, essentially, is a way to... It's like a gate, in a sense. You press on the base with a voltage, and then that allows current to flow from the collector through the emitter. So if there's a signal that comes into the base, then it will allow current to flow from collector through emitter into the motor, and the motor will begin to spin. So now let's get some code to get this working. All right, so let's go to the code. We're under microbit 3, and let's go to write analog pin P0. Go to output. Where is it? Where is it? All right, write analog pin 020 under the plot bar graph that we used before, and then write analog pin again. So let's see, right here, write analog pin again, select input, and then read analog pin 0. So read analog pin 0 to the 0 spot on the code blocks. So we're reading 0, so we're reading the voltage of the, or we're reading how many bits are going to pin 0. And then we'll change P1 or P0 to P1 and P0 to pin 2. So pin 1, pin 2. So pin 1 will turn the motor on, pin 2 will turn the LED on. All right, so let's hit continue. When you're ready, start the simulation, rotate the potentiometer dial to see how the LED and motor react. All right. So right now we have 66 RPM. Goes down to 0 RPM. And then we turn it all the way up, all the way down. So as we adjust the potentiometer, it adjusts how fast our hobby motor spins and also how much light goes to our LED, so how bright the LED is. So pretty cool. All right. Let's go back to the project page, everybody. Go to Tinker Circuits, more tutorials. All right, so the last thing that we will do is using microbit with a breadboard. All right, so we have some different LED circuits. It's fun to wire directly to the microbit, but there's a limit to the number of components that you can add via direct wiring. All right, so in this one, we're going to basically make some different external LED circuitry to power some LEDs. So this should be a rather simple example. So let's go ahead and just start the simulation. It's a blink LED, so when you click the button it blinks. And then traffic lights, very similar to the Arduino Uno that we messed with earlier. Alright, so let's go ahead and build our own copies. So we put in the microbit, put in the breadboard, rotate it. Okay. And let's go ahead and create a wired connection from pin 0 to A2. All right. So let's go ahead and select a resistor now and rotate it. We'll cross the gap here and we'll go from D2 to F2. We'll make it a 470 ohm resistor. Change it from kilo ohms to ohms. And then we'll go LED, rotate, keep rotating. So we have the anode in J2 and the cathode in J3. And then we go from cathode to the negative strip and from negative strip to ground. Okay. And so now let's go ahead and go to the code. Go to microbit 3. We're going to throw on start into the trash, and we'll do forever. We'll do go to output, and we'll go to digital write pin 0. So digital write pin 0 to high. And then we'll go back to basic, and we'll wait for 1 second. And then we'll do a digital write pin again. So let's go back to output and digital write pin P0 to low. And let's go ahead and go back to basic, and we'll wait for 300 milliseconds. And then let's start the simulation. So it blinks for 1 second on, for 1/3 of a second off. Okay? So now we'll create the traffic lights. So let's go ahead and draw a wire from P1 to a new terminal strip row. We'll go P1, pin 1, and we'll go to B5, yellow. Change that one to red to match. And we'll go from pin 2 to B8. Change that one to green to match the LED colors. We'll Control C, and we'll go across the bridge there from D5, and then from D8 we'll go ahead and Control C our LED and make that one yellow. And then we'll Control C, Control V on Windows and make them green. And then we'll go to the ground strip. Okay, so now we go to our code. And let's go ahead, and we've got everything wired up. So now what we need to do is we need to basically copy and paste this 3 times for pin 0, pin 1, and pin 2. Alright, so we'll digital write the red light on for 1 second, and then we'll wait. And we'll turn it off. So let's think through this. So ultimately, we need to turn on P0, red light, on for second. And then we need to turn it off. And then we need to turn the next one on and then the next one off. So let's go ahead and do outputs, and we need to set, when the red light's on, the others need to be off. Okay, so they're on. So the red light's on for 1 second. Okay, and then we go P0, we go low. The yellow light turns on. and the green light stays off in the low state and will be yellow for half a second, or 400 milliseconds. And then finally we go P0 goes low, yellow light P1 turns low, and then the green light turns on high. And we need to wait, and we'll be green for 1 second. And then it'll loop, and let's just see if that works. So it goes red, yellow, green. Just for curiosity's sake here, let's see. So we did a little bit different than what they did, but it still works. So something to play around with for sure. And you know, we're a little bit over an hour in here, and ultimately we made it through about half of the tutorials. So I think this is a good stopping place for now. And I want to thank you for joining me. Please subscribe if you haven't already. A lot of you out there just watch the videos. Really would appreciate subscriptions. So I hope you have a great day. And come back with me to learn more, and we'll go and do a deep dive into Arduino here on Tinkercad.